And I suppose that's enough time. You've had time to read the comic. I would hate to start doing these videos and neglect you of the comics. Some of you may not like them. Others may look forward to them each day. I don't know. But if you need more time to read the comic, that's fine. Pause the video. Otherwise, here we go. Section 5.1, Estimating with Finite Sums. Now today we begin our new approach, our antiderivative approach, or integral approach, if you will. When you talk to people about calculus, most people break up calculus into two main branches, differential calculus and integral calculus. We have already dealt with the majorities of differential, although mind you, for all we've studied, there's 1,000 things more out there that we could study for differential calculus. Today we begin looking at integral calculus, and we do so with 5.1, Estimating Finite Sums. Today our state standards, our objectives, will be to calculate the distance traveled with varying velocities. You know, we can all do velocity or distance traveled with a constant velocity, d equals rt, but what happens when it varies? Well, look at that. We'll talk about the RAM approach, rectangular approximation method. Now that's mainly a calculator method that you'll have to do when you get into class, but I will show you that when you get into class tomorrow. We'll also talk about how this approach can be used to calculate the volume of a sphere, and then we'll use a medical approach. We'll look at how this can be used to calculate cardiac output. Very, very significant that we get this down. This is the foundation for integral calculus. So let's begin. Example 1. Finding the distance traveled when velocity varies. So here's our situation. A particle starts at x equals 0. It's moving along the x-axis with a velocity v of t equals t squared. Where's the particle at time 3? At times t equals 3. Now some of you may be tempted at this point to just plug 3 in and say, okay, v of 3 is 3 squared 9. 9 is the answer. Well, that's not exactly correct, because what that tells us is what is the velocity at time 3. It does not actually tell us how much distance has been traveled. So we need a new approach. Well, here's my approach. I'm going to start out by graphing the function, and I'm going to break that function up into 1/4 subintervals. So we have x squared here, or t squared if you will. So I take t squared and I graph it. Here's my parabola. Now notice that I only deal with the right side, starting at 0. Why was that? Because I start at x equals 0 and I'm moving along to 3. Although I guess technically it should be t equals 0, not x equals 0. So I'm just dealing with 0 to 3, and I've broken it up, each part, into 4 equal subsections. Now, just to give you an idea of where we're going with this, what we're going to do is we're going to take this and we're going to find its area. Because if I consider this x-axis down here to be time, and I consider the y-axis to be velocity, that's rate times time, and if I can figure out how to combine these two things together, velocity and time, rate and time, I'll have distance. So how are we going to find this area? Well, I don't exactly have formulas for areas of these rectangular-like shapes, but you see they're curved. So how do I do that? Well, the next thing I'm going to do is, again, I'm going to recognize that the area, distance covered of each interval, would be found by multiplying the height, velocity, by the width, time. Well, we know that's basic area. Width times height. Width times height equals the area. Now, let me move my box down here a little bit so you can see the bottom of the screen. The width of each section is 1/4. We know that from the beginning. We set that up, right? The width of each section is 1/4. That's how we knew to put 4 in between each number. So the width of every rectangle here is 1/4. Now we need to convert each section to a rectangle whose midpoint touches the function. Remember, we couldn't deal with the curve. We don't know how to deal with the curve, but we can take out the curve, and instead we can use these little rectangles to approximate. Now, I understand right now at the beginning this is not going to give us an exact answer. This will only give us an approximation. Now, we're going to use the midpoint to find the height of each box. What do I mean by that? Well, remember the vertical axis here represents velocity. So if I can find the height, the vertical height of each box here, I have the height for area. Well, to find that height, what I need to find is I need to figure out, well, what is the value of the function, for instance, right here? What is the value of the function right here and here and here and here and here and so on? So if I can find that, then I can find the area. So let's calculate the area of each box. Okay? here's what we're going to do. First of all, I'm going to take each of these sub-intervals. Remember, we took and we broke up in each area or each distance of 1 into 4 equal parts because we had a partition of 1/4. So the first sub-interval starts at 0 and goes to 1/4. The next one goes from 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1, and we'll have more to come, but let's go ahead and deal with these. Now, what is the midpoint of 0 to 1/4? Well, add those two numbers up, divide by 2, 1/8. The midpoint of these two, add them up, divided by 2, is 3/8. Here you would have 5/8, and there you would have 7/8. And if you're noticing a pattern, that is actually a pattern that you could follow. 1/8, 3/8, 5/8, 7/8, 9/8, and so on. Now, how do I find the height? Well, remember, to get the height, you need the value of the function at a given point. Well, our given point is the midpoint. So to find the height, I'll plug the midpoint into the function. 1/8 squared, for instance, would be 164. So the height of the first rectangle that we had was 164. The height of the next rectangle will be 3/8 squared, which would be 9/64, 25, and 49/64. Now remember that the width of each rectangle is 1/4, or the base, if you will, is 1/4. So if area equals base times height, the base would be 1/4. The height would be what we have here. So multiply each of these numbers by 1/4, and we have there, 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 and there. So from 0 to 1, if you will, see here, starting at 0, going to 1, I had 4 rectangles. Here is the area of each rectangle. Now I'm going to repeat this process twice, one time going from 1 to 2, and the next time from 2 to 3. I'll go through these very quickly. If you want to work them out yourself and see the numbers, pause the video. Alright, our next intervals are 1 to 5/4, 5/4 to 3/2, 3/2 to 7/4, 7/4 to 2. Now, find the midpoint the same way. Add each of these up, divide by 2. We get these midpoints. Remember, to find the corresponding heights, you plug these in and square them. Right there. And then to get the corresponding areas, each of the heights times 1/4. There, 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 and there. Alright, now again, if you need more time, pause the video. Otherwise, I'm going on. Now, we still need to do 2 to 3. So 2 to 9/4, 9/4 to 5/2. And you may say, well, how am I getting these numbers each time? Well, remember, going by 4. So if you take 2 and add 1/4, you get 9/4. 9/4 plus 1/4 is 5/2, and so on, if you're not real sure how I got those numbers. Midpoint of each, add them up, divide by 2. There, 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 and there. Height, we square each of those. And then for the area, you multiply each of those by 1/4. So again, pause the video if you need. Otherwise, we go on. Now, what do we do with all these numbers? Well, here are all of the areas that we calculated up to this point. As they come in, it looks like we got a, there we go. When you take all these areas, you add all of them up, you get this number here, which is about 8.984. So the particle has moved almost 9 units in 3 seconds. Now, the reality is, it actually does move exactly 9 units if you calculate it correctly. Now, that is just a coincidence. If you're saying, well, you told me I couldn't plug in 3 earlier and 3 squared was 9. That just happens to be a coincidence on this problem. It doesn't normally work out that way. Okay? So finding the total distance traveled. Now, let's move our screen back up. Got to go back. Hold on one second. I had a mistake here. Let me go back here. And let me move my screen up so that you can see the top of the screen there. Now, our calculator will take care of a lot of this stuff for us. All that little nitpicky work we were doing about adding, dividing by 2, multiplying, so it will do this stuff for us. It's called a RAM program. RAM standing for REM, Rectangular Approximation Method. You see right here, Rectangular Approximation Method. Now, usually these RAMs are broken up into 3 parts. You can do left point RAM, or LRAM, right rectangular approximation method, or RRAM, or midpoint, which is MRAM, right here, LRAM, MRAM, or RRAM. Now, if we were to work this out with our calculators, it actually goes much faster. Now, just to give you an idea, LRAM is based on this graph right here. You see where the height of each rectangle is found not by the midpoint. That would be this one right here. That's what we actually worked out by hand. We did MRAM. We found the midpoint height. LRAM finds the height of each rectangle using the left endpoint, whereas RRAM right here, you see, finds the height of each rectangle using the right endpoint. Now, At home, you're not going to be able to do this. You'll have to, again, do this at home, or I'm sorry, at school once you get with one of my calculators. I do have this program loaded on our calculators, and I will show you how to use it tomorrow. But just to show you what happens, what you'll do is we'll take this problem, we'll work this problem right here. What you'll do is you'll tell your calculator to enter in this equation, x squared sine x. You'll tell the LRAM, MRAM, whatever RAM program that this is your function, and you'll give it this interval right here, 0 to 3. And then you'll tell it how many sub-intervals you want. Now remember, we broke up into quarter width sub-intervals, so we ended up having, I think it was 12 sub-intervals last time. Well, 12 was about as much work as we wanted to do and then some. But with this calculator, we can do 5, 10, 25, 50, 100, 1,000, 10,000, a million sub-intervals. And we can make those rectangles real small, because the fact is, the smaller you make the rectangles, the less error you have, so that if you could find a way to make them infinitely small and use infinite many rectangles, you would actually get the exact answer and not just an approximation. But when we put all this information into our calculators, which we'll do tomorrow, you get this table here, and again, I'll move the screen down so you can see the bottom. We get this information here. You see 5 subintervals. It's this, using L, M, and R. All the way down to 100 subintervals, we get these numbers here. All of these are approximations of the area underneath this curve by drawing rectangles. This one would draw 5 equally spaced rectangles. This one would draw 50, so you can imagine they'd have to be considerably smaller than the 5. And so on, etc., etc. Alright, now let's use this in a problem. Let's estimate the volume of a sphere. Now we all know how to find the volume of a sphere. 4/3 power cubed. Not a problem. Not a problem. But if we did not have that formula, if we didn't have a way to approximate it with that formula, we would need another approach. So here's what we're going to do in our approach. Let's start out with a semicircle of radius 4. So here's our semicircle right here, radius 4. Now why a semicircle? Well, that's fairly obvious, because that's the basic shape of the sphere if you just go along one edge. Now here's where we need to think three-dimensionally. I'm going to take that semicircle here and I'm going to revolve it. In other words, if you can imagine, it's going to come out of your computer screen and it's going to circle around back into the computer screen, and it's going to look something like that. Now, here's what we're going to do, and this is going to be interesting. Before, when we were finding the area under the curve, we broke it up into flat rectangles and we found the area of each rectangle. Well, that doesn't exactly help me here if it's a three-dimensional object. So what I'm going to do is I'm going to break up my sphere into cylinders. You see the cylinders here. Here's one, and here, and here, and here, and here, and so on. I'm going to break it up into cylinders because I do know how to find the volume of a cylinder. The volume of a cylinder is pi r squared h. Well, for our problem here, the radius just represents some amount of x here, right? I'm sorry, not the radius, but the height just represents some amount of x. See, the height of the sphere would be from here to here, and it just represents some x value. The radius, however, from here up to here, you see, there to there is a vertical climb, so that's the y value. So instead of pi r squared h, you see I have pi y squared h. And then what that will allow me to do is it'll allow me to take this radical 16 minus x squared and plug in for y, so that what we end up with is not pi y squared h, but we would have pi times the square root of 16 minus x squared h. Well, again, what did we say the h was? We said the h was the height, or it was x, some value x. And then if we simplify that, we have pi times 16 minus x squared times x. Notice all it did was it got rid of the radical. Now I'm going to pause right here for a second because I see that my 15-minute time limit for this first video is almost done. So I'm going to get ready to stop it, and then we'll come back to this point right here. So give me just 1 second, I'll get the next video started.